So Newton's second law relates the net external force on an object to that object's acceleration. So it gives the relationship between forces and motion. It describes how forces create an acceleration, which then creates motion. So it says that the net external force on an object is equal to the mass times the acceleration. Newton's second law only works in inertial reference frames. So again, it's very important to note that the F in this equation is the net external force that you get from taking the vector sum of all of the external forces. It's not just a single force. So if you rearrange this equation for the acceleration, you can see the role that mass plays. For an object with more mass, you need a greater external force to get it to have the same acceleration than if it was an object with less mass. So this is consistent with the idea that mass is a measure of inertia. So objects with more mass have more inertia, and therefore you need a greater force to have the same acceleration. So also notice that this equation is involving vectors. The net external force is a vector, and so is acceleration. Acceleration is being multiplied by the mass. But we know that when you multiply a positive scalar times a vector, then it doesn't change the direction, it only changes the length of the vector. And so since mass is always positive, that means it's not changing the direction of the acceleration vector, and therefore the acceleration and the net external force vectors always point in the same direction. The direction of the net external force, that's the same direction as the acceleration of the object. And also we can see that Newton's first law is really just a special case of Newton's second law. If the net external force is 0 on an object, then that means the acceleration has to be 0 according to this equation, and so the object will continue to travel at a constant velocity. As an example, we can find the force of gravity on any object near the Earth's surface. So in kinematics and projectile motion, you learn that any object has a downward acceleration of g, which is about 9.8 meters per second squared. So if we replace the acceleration with g in Newton's second law, we can find that the net external force on that object must be m times g, if the only force on the object is gravity. And here g is written as a vector because the acceleration is a vector, so this would be just pointing downwards towards the center of the Earth. That's always the direction of the gravitational acceleration. And so the force of gravity on an object is called its weight. So the weight of an object is its mass times g near the surface of the Earth. More generally, it's just the force of gravity. So you can see that the mass of an object never changes, but the weight can change depending on how hard gravity is pulling on the object. So also from the formula, you can see what the units of a force are. So we have mass times acceleration, and we know mass is kilograms, and acceleration is meters per second squared. So that means the units of force are kilograms times meters per second squared, which we call a newton. 1 newton is the amount of force you need to accelerate 1 kilogram mass at 1 meter per second squared. So as a simple example of applying Newton's second law, say you have a 10 kilogram box and you are pulling on it with a 50 newton force that's going to the right at a 30-degree angle above the horizontal. So we want to know, the acceleration of this object and what the normal force on it is. So to do this, it's easiest to break the net force on the object into its x and y components. That way we can work with the x and y equations separately. In the x direction, the only force is the component of that 50 newton force, which is equal to 50 times the cosine of 30 degrees. In the y direction, we have the normal force and the component of the 50 newton force that are pointing upward, and then we have gravity, which is pointing downwards. We set the net force in the y direction equal to 0 because we know it's not accelerating in the y direction. If you're pulling a box, it's not going to start flying up into the air. So we know that the acceleration in the y direction has to be equal to 0. In other words, the net external force in the y direction on this box is equal to 0. So using that, we can solve for the normal force just by moving everything else to the other side. And you can see in this situation, the normal force is not directly canceling gravity. In many situations, we just say the normal force is equal to an opposite direction of gravity. But here, since you have an applied force, the 50 Newton force, which has some y component, the normal force changes because of that. If the 50 Newton force wasn't there, then the normal force would just be equal to mg, 10 times g. But here it's less because of that y component of the 50 Newton force. Because if it was still 10g, then there would be a net force in the positive y direction. For the acceleration in the x direction, we can easily solve for it because there's only one force involved. And so you can easily use a calculator to get the values. So now we can look at Newton's third law, which says that if two objects are interacting, say they're touching or something, then they exert forces on each other that are equal in magnitude and opposite in direction. So if one object exerts a force on another object, then that object exerts a force back onto the original object, which is exactly the same magnitude and exactly opposite the direction. So say these two objects are colliding. So the ball 1 exerts a force on ball 2, and ball 2 exerts a force on ball 1. They have the same magnitude, they're just opposite direction. So mathematically, you can just write the force of 1 on 2 is equal to the negative of the force of 2 on 1, and these are both vectors. So this also works with long-range forces such as gravity. So when the Earth exerts a force on some object, then that object exerts a force back on Earth. So gravity is really a two-way thing. Except the reason that the object will fall to the ground and the Earth doesn't move at all is because obviously the Earth has a lot of mass. If you give so even though the force that the Earth exerts on, say, an apple is the same that the force that the apple exerts back on the Earth, since the Earth has such big mass, it'll have a very tiny, almost zero acceleration due to that force, whereas the apple will have a very large acceleration. So in the last example, we have two blocks of different mass. When one is denoted with a little m and one with a big M, there is a rope connecting the two blocks, and we are pulling with a force on the bigger block to the right. So we want to know what the acceleration of the system is and what the tension in the rope is. So to find the acceleration of the system, we can treat the two blocks as one big system, basically one big block, because the two blocks have to have the same acceleration, because they're connected by this string. If the first block had a bigger acceleration than the second block, then that wouldn't make sense. They couldn't keep moving together. One of them would fly away. So the two blocks must have the same acceleration. So when we talk about the acceleration, we're not talking about the acceleration of just one block, we're talking about the acceleration of the whole system. And so again, we treat the two blocks as one big block, and so when we do that, the tension in the rope becomes an internal force. So the only external force that we care about is the force that's going to the right. We just assume that the normal force and gravity are canceling out. We don't care about those. So we have F equals, in this case, the mass is going to be the mass of the two blocks combined times the acceleration. So all we have to do is move it to the mass to the other side, and we find that the acceleration of the system is going to be F over the combined masses. So now that we have the acceleration, we can find the tension in the rope. And remember, the tension in the rope is just how hard the rope is pulling on each block. So let's focus on the big block of mass capital M. So we have force F to the right and the tension to the left. So the net external force is going to be F minus T, because we're assuming right is positive and left is negative. So F minus T is equal to M, capital M, times its acceleration, which we just found. All we have to do to find the tension is move everything to the other side. And if you combine the fractions using the common denominator, then this is what you get. The little m times F over M plus big M. So we could have done the same thing focusing on the little block. On the little block, the only external force is the tension in the positive direction. So the net external force is T, and that's equal to little m times the acceleration. And you can see that you get the same answer as you did for the big block. So the tension for both blocks is the same in this situation. It's pulling on both blocks with an equal force.